Hi students, this is Viswanath, chemistry faculty for NEET and IIT exams. In last class, we completed numericals related to van der Waals equation of state. Now see the next one, liquefaction of gases. The liquefaction of a gas takes place when the intermolecular forces of attraction become so high that they bind the gas molecules together to form the liquid state. Say this, liquefaction means a gas is converted to liquid. That process is called liquefaction. When this process takes place, when the intermolecular forces between the gas molecules are very high, then that gas is converted to liquid. That means liquefaction takes place. The van der Waals constant A is a direct measure of magnitude of attractive forces between the molecules. In the previous concept, we completed van der Waals equation of state. In that, two constants are there, small a, small b. Small a is a measure of magnitude of attractive forces between the gas molecules. These attractive forces are high, then gas can be converted to liquid. That means greater the value of A, more easily the gas is liquefied. So this A value is more, attractive forces are also more, then that gas can be liquefied easily. A gas can be liquefied by cooling or by application of pressure or the combined of both. If we want to convert a gas into liquid, what we should do? We should cool it. That means we should decrease its temperature or we should apply more pressure. Otherwise, both. By decreasing temperature, by increasing pressure, we can convert a gas into liquid. Between these two, temperature and pressure effect, the effect of temperature on the liquefaction of gases is found to be very important. So in these two, pressure and temperature, temperature is very important because as higher the temperature of the gas, more difficult it is to liquefy it and higher is the pressure required. So the gas is present at a high temperature, then liquefaction process is difficult. That means at high temperature, if a gas is present, then we should decrease its temperature and also more pressure is required. That's why temperature is more important factor in the liquefaction of gases. Now see the next one. Critical temperature. The temperature above which a gas cannot be liquefied, howsoever high pressure may be applied on the gas. So at a particular temperature, for a gas at above a particular temperature, it cannot be converted to liquid. However, high pressure may be applied. Above a particular temperature, even though by the application of high pressure, a gas cannot be converted to liquid, that temperature is called critical temperature. Understand carefully. The temperature above which a gas cannot be converted to liquid even after applying high pressure, that temperature is called critical temperature, represented by Tc. So critical temperature is the maximum temperature above which a gas cannot be converted to liquid. Below that critical temperature, we can convert that gas into liquid state. Okay. Next, critical pressure. The pressure required to liquefy the gas at the critical temperature is called critical pressure. So above a particular temperature, we cannot convert a gas into liquid. That is called critical temperature. Under that critical temperature condition, we need to apply some pressure for the liquefaction. That is called critical pressure. So critical pressure is represented by the symbol Pc. Next, critical volume. The volume occupied by 1 mole of the gas at the critical temperature and critical pressure is called critical volume. So under critical temperature and critical pressure, 1 mole of the gas having a particular volume, that is critical volume. represented by Vc. So critical temperature Tc, critical pressure Pc, critical volume Vc. All the three collectively are called critical constants of the gas Tc, Pc, Vc. Example, for CO2 critical constants are Tc equal to 30.98 degrees Celsius, in Kelvin scale 304.10 Kelvin. Pc critical pressure 73.9 atmosphere, critical volume Vc 95.6 centimeter cube per mole or 0.0956 decimeter cube per mole. So these are the critical constants for CO2. Next, critical temperature of a gas is the highest temperature at which liquefaction of gas first occurs. Okay, so below that particular temperature liquefaction starts, that is critical temperature. Next, at critical temperature, liquid phase passes into gaseous phase imperceptibly and continuously. Imperceptibly means identifying is very difficult. That means very little we can notice. To a small extent, a liquid phase is converted to gaseous phase, or imperceptibly means we cannot identify clearly, but it takes place. So at critical temperature, liquid phase passes into gaseous phase. Next, supercritical fluid. The dense fluid obtained by compressing a gas above its critical temperature is not a true liquid, but behaves as liquid in many aspects. It is called supercritical fluid. Okay, now come to this. Take a gas above its critical temperature. If we apply pressure, then it can be converted to a liquid, but actually it is not a liquid, but it exhibits many aspects of the liquid. That's why it is called supercritical fluid. So the dense fluid obtained by compressing a gas above its critical temperature. Okay, keep it in mind. Supercritical fluid is not actual liquid. It resembles to liquid, so it is called supercritical fluid. Supercritical fluid can be used as a solvent. Example, supercritical CO2. So carbon dioxide critical temperature 30.98 degrees Celsius. Above this temperature, under 600 bar pressure, we can get supercritical CO2, supercritical fluid of CO2. At this temperature and pressure, this supercritical CO2 is used as a solvent for the extraction of caffeine in the manufacture of decaffeinated coffee. So generally in tea and coffee seeds, caffeine is present. If we want to remove that caffeine, then we can use this supercritical fluid of CO2. So to remove the caffeine from coffee seeds to manufacture decaffeinated coffee, we can use supercritical fluid of CO2. Next, Joule-Thomson effect. When a real gas is allowed to expand adiabatically from a region of high pressure to a region of low pressure through a fine hole, it is accompanied by cooling. This phenomenon is called Joule-Thomson effect. A real gas means anything. O2, N2, NH3, CO2, CO, any gas is allowed to expand adiabatically. That means no transfer of heat between system and surroundings from high pressure region to low pressure region through a fine hole. Then that gas undergoes cooling. This effect is called Joule-Thomson effect. That means when a gas is allowed from high pressure region to low pressure region, we can observe cooling effect of that gas. That is Joule-Thomson effect. Now say this. Next, inversion temperature. The temperature above which a gas shows heating effect and below shows cooling effect is called inversion temperature. Observe carefully. So above a particular temperature, a gas shows heating effect. Below the same temperature, same gas exhibits cooling effect. So that temperature is called inversion temperature. That means it shows different effects above that temperature and below the same temperature. At inversion temperature, the gas shows neither heating effect nor cooling effect when allowed to expand adiabatically. At inversion temperature, that particular gas does not show any cooling effect or heating effect. Most of the gases have high inversion temperature, much higher than room temperature. So we have different gases, oxygen, nitrogen, NH3, CO, CO2, different types of gases are there. All these gases have inversion temperatures. Their inversion temperature values are higher than room temperature. Okay. Now see the important question. Hydrogen, helium and neon gases show warm up in Joule-Thomson effect. Explain. What is Joule-Thomson effect? When a gas is allowed to expand from high pressure region to low pressure region, it undergoes cooling. But these three gases undergoes heating in Joule-Thomson effect. What is the reason? Say this very simple reason. All the gases except H2, helium, neon have high inversion temperatures. Except these three gases, remaining all the gases have high inversion temperatures. So when those gases undergo Joule-Thomson effect, they show cooling. But H2, helium, neon inversion temperatures are low. Without cooling these gases means H2, helium, neon, below their inversion temperature, if they undergo Joule-Thomson effect, they get warmed up. So understand carefully. Helium, hydrogen, helium, neon, these gases without decreasing their temperature below their inversion temperature, if they undergo Joule-Thomson effect, they get warmed up. That is the inversion temperature definition. Above a particular temperature, gas shows heating effect, below cooling effect. Now for these three gases, inversion temperature is very low. At room temperature condition, if we conduct Joule-Thomson effect for these gases, that means above their inversion temperature, then these gases get warmed up. But if these gases are first cooled to a temperature below their inversion temperatures and then undergo Joule-Thomson effect, they also show cooling effect. So what is the reason for this? Hydrogen, helium, neon get warmed up in Joule-Thomson effect due to their low inversion temperature. Okay.